What's good, y'all? Welcome back. In this video, we are concluding our introduction to eigenvalue problems by completing the last step in our process of mathematizing the couple pendula problem. Recall in steps 1 through 4, we transformed a coupled pendula problem, so two pendula hanging from the same stable support structure, where the masses are moving back and forth, connected by a spring. We want to solve this problem to produce function descriptions u1 and u2 that will let us determine the location of the center of mass at any time t along the ruler, so project those things down. And at the beginning of step 5, in other words, at the end of steps 1 through 4, we have this equivalent realization of the coupled pendula problem. Specifically, we have it in matrix form, where we're taking a matrix M, called the mass matrix, multiplying it by the second derivative of the vectored value displacement functions, aka this is mass times acceleration in vector form. And then we equal that to negative k times the displacement function that we so desired. The actual values of each of the entries of these matrices are spelled out here. This matrix we're going to call the stiffness matrix to correspond with work that we've done previously. This matrix is the mass matrix. It's diagonal. The diagonal elements are positive since the masses on the end of each chord in the pendulums are non-zero. This matrix vector equation encodes Newton's second law, specifically mass times acceleration is equal to the net force acting on each object. This is in higher dimensions because instead of studying a scalar valued phenomenon, one with only one component, we're studying two components in the same system that are coupled together. The net forces came from the analysis that we did in the last video. And in our work, we're searching for our unknown and desired displacement functions, u1 and u2, that solves this system written in this compact form. When we created the system, we actually factored out a negative of the stiffness matrix. And the reason that we did that was it allows us to bring all terms on one side. This m u double dot of t plus k u of t is a matrix equation. However, it has a very nice analog in scalar space, which is the undamped, unforced, simple harmonic oscillator equation. In this case, it is a two-component equation, but it is identical to the scalar version. Specifically, if we just turned m, k, and u into scalar valued objects, that would be the undamped, unforced, simple harmonic oscillator for one mass. In all of our work, we've claimed that we can transform the coupled pendula problem into a standard eigenvalue problem. To do so, let's start with the Newton's second law. Mass times acceleration is equal to the net force acting on each mass. Our goal in this work is to create a standard eigenvalue problem, not a generalized eigenvalue problem. And thus, we're going to assume that the two masses are identical. In other words, m1 is equal to m2. The moment that we do that, why don't we just call each mass m? So m1 and m2 are identical. That means this matrix is a scalar multiple of the identity. When we see this, we know that each of those diagonal elements is non-zero and thus positive because they measure masses. There's no such thing as a negative mass. This is a diagonal matrix with non-zero diagonals that are identical. That matrix must be invertible. The statement that the matrix M is invertible is identical to saying there exists an inverse to M. Specifically, we could multiply both sides of that equation by M inverse. M inverse times M, that goes to the identity. Identity times the second derivative of U leaves the second derivative of U. On the right-hand side, when we multiply on the left by m inverse, we get negative m inverse times k times the desired displacement function. Of course, one of the really nice things about matrices and vectors is we can write them in general form, or we can specify entry by entry. If I look at this matrix M, where we've assumed both masses are the same, something we can design in the McCusker apparatus, the inverse of that diagonal matrix is a diagonal matrix with the reciprocal elements on the diagonal. In other words, 1 over m on the first diagonal and 1 over m on the second main diagonal, which implies that we have this acceleration vector on the left-hand side equal to the negative m inverse times k. K hasn't changed. And then over here we have our displacement. Of course, we can just get the product of m inverse times k using simple matrix multiplication. In other words, take row 1 multiplied by column 1, take row 1 multiplied by column 2, take row 2, column 1, row 2, column 2, and that would give me the entry by entry definition. And in fact, that's exactly what we've done here. When I multiply the first entry by 1 over m, the m's cancel out in the first term, and then I have k over m in the second term. When I multiply 1 over m by the entry 1, 2, I get negative k over m, and the same pattern happens in the second row of that matrix, which means that my coupled pendulum problem has been transformed into finding a set of functions u1 and u2, such that the second derivative of those functions is equal to this matrix multiplied by the functions themselves. And this is where we're going to introduce some simplifying notation. Specifically, we're going to say, hey, this matrix is really kind of special. Let's give it its own name. Let's call that capital A, as in the standard eigenvalue problem. We can restate our problem. The second derivative of our desired displacement function is equal to negative a times u of t, where a is m inverse times k. In other words, when we're trying to figure out what the motion of the pendulum is, here we have this video where we're looking at the center of the masses, the two pendulum are coupled, and we're trying to figure out how do these things displace over time. We're claiming that if we can find functions u sub 1 and u sub 2, which are functions of t that give a concrete representation of the displacement of these masses in this video, that problem is equivalent to solving this mathematical problem, which is finding functions that satisfy the second derivative is equal to negative a times u of t, where a is defined by the mass matrix times k. Before we go further into the theory, I want to talk about some of the engineering components, or what you might call real-world considerations, that we're going to make here. Specifically, in practice, we're not trying to predict the behavior of these masses for the rest of time. In theory, we will get to a place that we can do that in ideal considerations, but in practice, we have some very specific time frame that we're going to focus in on the masses. So for our case, when we're looking at this video of mass dynamics, this video is only 2 minutes and 56 seconds long. We might determine that if we could match the behavior of some subset of those videos, some number of frames in that entire video, we would call that a successful model. So the question that we ask ourselves is, for this 2 minute and 56 second video, we're going to observe the dynamics, and we're going to say for some start time and some end time, let's try to get those u sub I, u sub 1, and u sub 2 of t functions to match the identical behavior observed in that time frame. So maybe we say, okay, let's start our video processing at 32 seconds. And then from 32 seconds all the way to, I don't know, maybe a minute long, so a minute and 32 seconds, we'll try to match all the displacement behavior of our particular masses in that time interval. So in other words, we're going to limit our focus. Instead of saying for all of time, we're going to say from 32 seconds in our experiment to a minute and 32 seconds in our experiment, 60 seconds of time. Let's see if we can match the behavior observed in the experiment video with the model prediction on that time frame. The next thing we're going to do in the practical problem of trying to match up theory and data is actually peg a reference position or a reference time so that we can match the data that we start with the observed phenomenon. So specifically, we're going to say for some time within our observation, within the start time and the end time that we're trying to model, let's choose a reference time, and we'll call that reference time T naught. T naught, in engineering terms, we would say maybe that's the 0 position, so from that point forward. But we're going to keep it general enough in our notation to just say it is a reference time. It's sometime between the start time of observation and the end time of observation. In equalities, we would say the start time is before the chosen reference time, and that's before the chosen end time. For example, our observation goes from 32 seconds to a minute and 32 seconds, and maybe we say to ourselves, like, okay, let's split the difference and then just go to like a minute and 1 second. So we'll set our reference time to be the first frame that happens a minute and 1 second in to the video recording of these dynamics. So that is now our reference time, which indeed is in between the start time of 32 seconds and the end time of 92 seconds. We're now further refining our problem. So remember, the goal of the coupled pendula problem is to find functions u1 and u2 that predict the location of the center of mass at any time t within some observed time frame. So specifically, we would say, hey, I want to know the exact location of these black dots between 32 seconds and 92 seconds anytime. So I want to get that location modeled to a pretty darn precise value within that time frame. The reason that we chose a reference time t naught, in this case that was 61 seconds into the modeling, the first frame 61 seconds in, was to use as a reference point for the behavior of masses in time. It allows us to say, at that point in time, we're going to say that we know both the exact location and the velocities of both masses as they travel. In other words, we're trying to solve differential equations, and a differential equation by nature is an equation involving a derivative. One of the things that's interesting about derivatives is that they involve change. So the whole idea of an initial value problem or a boundary value problem is I know how something changes, and if I have some information about reference position sometime during my observation, then if I know where it is at a specific time and I know how it changes, perhaps then I can predict where it is at any time. If I know where it is at some point in time and I know precisely how it changes, then I can predict the location of those objects any time that I'd like within my observation period. So when we say that t naught is a reference, what we mean is at the chosen time frame, let's say that we could actually measure the exact position of each mass. In other words, I could use tracker, for example, to figure out the exact location of the center of mass given an imposed frame of reference and a calibration stick or a reference length. If I had the positions and I could figure out where the equilibrium position is, that gives me the exact displacement at the chosen reference time. Moreover, not only does this video give us access to what we call position data through our tracker measurements, but those data points can also be used to calculate a representation of what we call initial velocity or reference velocity. In other words, not only do we have u of t naught, but we also have u dot of t naught, the velocity of mass 1 at reference time t naught and the velocity of mass 2 at reference time t naught. Under all of these, we've assumed that the masses are actually changing their position, that the displacement data is not zero. That assumption is really important because if we had a mass system that literally was stuck in equilibrium, the solutions of those would be trivial. It would literally just be the displacement is zero for the entire time frame of my observation. The only time this problem is interesting is if one of those masses has non-zero displacement or non-zero velocity at some time, and then we want to know what happens for the rest of time. Then we're making the claim that figuring out functions that describe the way that those masses move is equivalent to solving this mathematical problem. And one of the questions we might ask ourselves is, well, what do we know about the underlying system that might help us get our head around how to solve this problem mathematically? This is where we can leverage all that psychological and emotional pain that we felt earlier in this lesson. Specifically, we've spent hours studying pendulums. These systems are just sets of coupled pendulums. Moreover, when we put these systems in motion, we're assuming small angle oscillations. We've already seen that small angle oscillations in pendulums give rise to this quote-unquote cosine phenomenon. Specifically, let's take a look at this system right here. Those masses are swinging back and forth in small angle approximation. I can promise you that the degree between the chords and vertical position is less than 7 degrees. In other words, less than 0.1 radians. If I look at that behavior and graph the displacement of those masses versus time, we get something that looks like a cosine curve. Let's put that in a way that's a little easier to see. So up here we have the vertical position, which we called equilibrium. Here we've got the red pendulum bob, and we're going to map the distance from the red pendulum bob to equilibrium. In other words, we're going to track the displacement over time. Let's put this pendulum in small angle oscillation, and then what we'll do is let's map that displacement over a time axis and actually show what that function looks like. So as we let that thing play out, notice that over time, that behavior looks like a cosine. The way that that thing oscillates back and forth, back and forth, back and forth, the displacement versus time graph looks as if it's a cosine. And in fact, we have this really interesting phenomenon when we couple the masses together. So if we don't let the spring extend at all, we think about the spring as not changing length, both of those pendulums kind of swing freely as if they were not coupled at all. That's called normal frequency 1 or normal mode 1. Up on top, let's imagine that we just turn those masses vertically and then we tracked the position. Notice that that thing indeed looks like a cosine. Now, of course, if we're doing it so that we turn the right down and the left up, positive direction goes in the downward position, so we got to check our references. But because we know the dynamics of single pendulums, we can start to get insights into what we might expect for the solution of our equation. In fact, not only in the case that they are completely coupled, they could also be anti-coupled. They could be anti-symmetric, and that's called normal mode 2 or normal frequency 2. That's what we see down here. In that situation, that the displacement of the right mass is the exact opposite at the exact same time as the displacement of the left mass, we get this cosine behavior. One is the opposite of the other, but indeed it kind of corresponds with what we would expect from a normal pendulum swing, a complete cosine curve discussing how those displacements move. That's what we see in both of those cases. In other words, when we're trying to get insights into how to solve the coupled differential equation, u double dot of t is equal to negative a times u of t, where u is a 2x1 vector encoding the displacements of each mass, we might say, well, what if we guessed each displacement, u1 and u2, was some scalar multiple times a cosine curve. So this scalar is going to be called the amplitude. V1 is a constant. It's a real numbered scalar. That's the amplitude of the cosine curve for the first displacement. V2 is the amplitude of oscillation for the second displacement. Inside we have this, what we'll call angular frequency. That's the Greek letter omega. And then we'll also say, oh yeah, by the way, this cosine curve has to be pegged to some reference time point in our measurement. In other words, at some point we actually have to know what is the displacement, what's the velocity, so that we can combine the equation for difference, aka the differential equation, with an initial reference point. If I know where I start and I know how I change, perhaps then I know the behavior over all time. In other words, we're going to make the assumption, let's assume that both displacement functions can be written as some scalar multiple times the same cosine curve. The scalar omega, it's not a W, it's kind of a curly W. That's a lowercase Greek letter. We read that out loud as omega. That's going to tell me how my cosine curve changes in time, and for those of you engineers, we call that the angular frequency. Notice that if I thought about the angular frequency as 2 pi divided by t, normally if I just had the cosine function, we know the period of the cosine function is 2 pi. If we think about the period of one oscillation, the amount of time that it takes the mass to go from a single position all the way through the motion back to that single position, that's not going to be 2 pi in general. And in fact, that's going to be a function of the masses, the spring constants, and the length of the pendulum. But we'll call that capital T. So one period of motion, what we call one cycle of motion, let's assume that that takes t seconds, which means after t seconds, I will have traveled the entire period. In other words, the angular frequency is the regular unadulterated cosine 2 pi frequency divided by the number of seconds that that mass takes to travel one full cycle in its swing. Let's say that in a different way. We're going to say, hey, if we want to solve this vector valued differential equation, this coupled differential equation, let's assume that the vector valued function u takes the form v1 times cosine omega t minus t naught, v2 times cosine omega t minus t naught. they're the same frequencies, they're the same inside function for cosine, and then the amplitudes might change. We're not sure about that yet, but the point is, let's make the assumption that each displacement function is just a scalar multiple of cosine. We know that cosine's a real valued function. These scalar amplitudes are scalar constant. Those are real valued. We can commute those. The multiplication swaps order, and specifically we can factor out a cosine at any time t. The output of this function is a scalar, so we're saying, hey, let's make a guess that the solution to our differential equation takes the form u of t is equal to a scalar multiple cosine omega times t minus t naught, the reference time, times some constant vector v. The fact that we've assumed that our masses are actually at motion means that these values v1 and v2 are not both zero. In other words, this is not the zero function. It's not like the masses just stay in place. These things are actually moving. In other words, we want to find a non-zero vector v such that u is equal to cosine times that non-zero vector in this form. This type of educated guessing has a long tradition, and in fact it has its own name. It's called the cosine ansatz. For you viewers that speak German, perhaps you want to translate ansatz for me. I've already looked it up online, but it would be nice to have a human being tell me instead. The point is, because we know information about how pendulums swing in the small angle oscillations, we're going to make the guess that our displacement function is scalar cosine function times some unknown v, and then we have to pay the price and suffer. What does that guess imply about our original problem? That's right. Mathematicians and engineers guess all the time. It's just that on the other side of the guess, there's a lot of grunt work that goes into it. So here we are. If we make the cosine nonsense, if we assume this is true, and we look back at our original equation, what could we say? But we know that the original equation, u double dot of t is equal to negative a times u of t. That involves a second derivative of u of t on the left-hand side. On the right-hand side, I just have a negative matrix times scalar. The second derivative of a vector-valued function, remember from multivariable calculus, when I take the second derivative of a vector, that is equivalent to taking the second derivative of each component of that vector. So the second derivative operator hits both the first component and the second component. On the right-hand side, we actually have the entry-by-entry definition of that matrix. With that, when we look at these individual entries, perhaps now we can use this cosine ansatz in its scalar form to figure out what that means in terms of the matrix equation. We'll do that by looking at both the left-hand side and the right-hand side separately, and we'll start by differentiating each individual displacement with respect to the implications of that assumption. The scalar form of our cosine ansatz take these forms. Let's go ahead and take the second derivative of either of these equations. To take the second derivative of that scalar equation, we actually need to take the derivative of the first derivative. Let's start with the first derivative. Assuming that the ith displacement is some amplitude times a cosine with an unknown frequency, when we take the first derivative of that thing, that's going to be the first derivative of a scalar multiple times cosine. We know in differentiation, the scalars come out, so I can pull the scalar v sub I out of that thing, and I'm just left with the derivative of cosine. When I take the derivative of cosine of omega of t minus t naught, this is with respect to the variable t. The derivative of cosine is negative sine, and then I have to take the derivative of the inside. Omega and t naught are both constants, so that means the chain rule allows me to bring an omega out, and that implies that the first derivative of the displacement is negative omega times v sub I, the amplitude of oscillation, times the sine of omega t minus t naught. Remember, the goal is to look at the left-hand side of our equation, which involves second derivatives. The second derivative is the derivative of the first derivative. This was the first derivative we just calculated. This is a differentiation operator with respect to t. Omega and v sub I are constant scalars. We can pull constant scalars out because derivatives are linear operators. That leaves us with the derivative of the sine function, but we know from calculus that the derivative of sine is cosine, and then based on the chain rule, we also have to take the derivative of the inner function. The derivative of a composition function is the derivative of the outer function evaluated at the inner function times the derivative of the inner function. So now I have cosine omega t, t minus t naught, times the derivative of the inside, which is just omega. The two omegas combined, that becomes omega squared vi times cosine. That negative came out because the first derivative of cosine was negative sine. It stayed negative because the derivative of sine is positive cosine. There's only one negative. Notice then, however, that the second derivative is a scalar multiple of the displacement function itself. This was because the cosine ansatz assumed that the displacement was v sub I times some cosine function. That's the exact term that shows up when we differentiate twice. So the second derivative of each displacement function is omega squared times the displacement function with a negative out front. But under the assumption that our cosine ansatz holds for both displacement functions, that implies the second derivative of u1 and the second derivative of u2 are literally just negative omega squared times u1 in that form, and then negative omega squared times u2 in that form, which means we can factor out a negative omega squared. We can commute, we can swap the order of multiplication. So now I have a cosine in the first term and a cosine in the second term, and then non-zero scalars v1 and v2. Pulling out the shared coefficients, I now have that the second derivative of my displacement vector valued function is negative omega squared times cosine omega t minus t naught times a non-zero vector v. Focusing in on the right-hand side, everywhere we see u, we can substitute with our cosine ansatz. So negative a times u of t is equal to negative a times the cosine omega t minus t naught times non-zero vector v. But of course, for each value of t, the cosine outputs a real value scalar. In other words, this is a scalar times a vector. On the outside, on the left, we have a matrix multiplication. But in matrix multiplication, if I have a matrix times a scalar times a vector, that comes out. That's one of the properties of linearity, which means negative a times u is actually negative cosine omega t minus t naught times a times unknown and desired non-zero vector v. When we relate those two expressions to each other, when we equate them, we see we're looking for scalars omega and non-zero vectors v that satisfy this new relation coming out of the work that we've just done. However, we want this to be true for all value of t during our experimental observation. This has to hold over all values of t in order for us to predict the displacement of each mass. Let's start with the easiest part of this equation. On both the left and the right-hand side, we see that there is a negative sign. Let's just divide each side by -1, and that disappears, leaving us to search for values of omega and non-zero vector v, such that cosine omega t minus t naught times omega squared times v is equal to cosine omega t minus t naught times a times v. We might be tempted to divide each side by cosine, except because it has to hold for all values of t, it should also hold when cosine is 0. We can't divide by 0. That approach doesn't actually hold weight here. Instead, what we do, let's bring the entire left-hand side over to the other side using subtraction. That's called rules of algebra. When we do so, we see the term on the right-hand side minus the term on the left-hand side is equal to the 0 vector. Both terms involve a scalar valued output of the cosine, so we can actually factor that out of our equation, and we're left with cosine times quantity a times v minus omega squared times v equal to 0. But this is a scalar times a 2 by 1 vector equal to 0. The only way that a scalar times a vector is equal to the 0 vector is if either the scalar is 0 or the vector is 0. That's called the zero product property for this vector space. But this relation must hold for all values of t. Cosine omega t minus t naught is not always going to be 0. Thus, in order for this product to be 0, it cannot be that this scalar is 0 for all values of t. In other words, we're going to focus our search to the term av minus omega squared times v, but we know more than that. Specifically, we know that the vector v is non-zero because we assumed that the masses were moving, that we don't have the trivial solution to the problem, which is both displacements have 0 value. There's actually some displacement that happens. There's some movement of the masses. Let's recap that in a different way. In order to solve this problem under the cosine ansatz, that will be true only if we can find non-zero vectors v such that a times v minus lambda squared times v is equal to the 0 vector. But if we bring this negative term over to the other side, we're looking for non-zero vectors v such that a times v is equal to omega squared times v. Let's go ahead and introduce some notation. Let's call omega squared equal to some new variable called lambda, lowercase Greek lambda. So we are looking for non-zero vectors v such that a times v is equal to lambda times v, where lambda is omega squared. Ding, 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 ding. This is a standard eigenvalue problem. We have now transformed the problem of predicting the location of the masses at any time into a coupled differential equation that looks like this. And under certain assumptions, we're claiming that is equivalent to analyzing the matrix A to find non-zero vectors and scalars in pair form such that A times V is equal to lambda times V. This is where I want to join you for some tears of joy and sorrow. Maybe tears of joy out of my left side and tears of sorrow out of my right side. We have just spent the last N hours in this lecture defining a coupled pendula problem and then translating that into a standard eigenvalue problem in the form AX equal lambda x. In other words, the entire focus of our work was to mathematize a real world context into a standard eigenvalue problem. We have just finished that. My hope is that this gives you insight into the type of work that it takes to make linear algebra come alive. Or another way to say that, the type of thinking and training and privilege required to turn things in the world around you into a form that you would recognize from the math classes that you take. This is a big deal, y'all. I wish I could write you a certificate. In future lessons, we're going to learn how to solve the eigenvalue problems and what that means for the corresponding coupled pendula problem. In other words, we're going to learn how to complete the loop in this modeling process. As a gift to my viewers, I challenge you. We just used the cosine ansatz to turn this differential equation into this standard eigenvalue problem. Please, viewers, use the sine ansatz. So instead of assuming that the displacement functions are a scalar multiple, cosine scalar multiple times some non-zero unknown vector v, assume the sine ansatz. U of t is equal to sine omega t minus t naught, the same omega, times some non-zero vector v. Show that this sine ansatz comes up with the same standard eigenvalue problem. I'm going to make a claim, and I could be lying through my teeth. The only way you'll know is if you check for yourself. Proposition. If I have a non-zero vector v that is called an eigenvector of this matrix, an associated eigenvalue lambda, in other words, if A times v is equal to lambda times v, then if I look at the vector valued functions, u of t is cosine omega times quantity t minus t naught, entire function output multiplied by non-zero vector v. And then I have a separate displacement function, u of t is equal to sine omega. These are the same frequencies, they're the same angular frequencies omega, t minus t naught times vector v. Both those displacement functions solve the second order linear system, u double dot of t is equal to negative a times u of t. In other words, information about the eigenvalues of the matrix A gives us deep intuition about solving the corresponding coupled differential equations, which gives us deep intuition about the behavior, the positions, the displacements of the masses in the coupled pendula problem. In the next videos, we'll talk about how to solve this type of eigenvalue problems by leveraging our intuition and knowledge about matrix algebra. I'll see you in the next lesson.